Now that we've discussed some of the basics of OSPF, let's see how an adjacency is formed between a couple of routers. Here we have R1 and R2, and we want to form an adjacency between these routers. We're going to start off where gigabit 0/1 on each of the routers are currently in a down state. That is the link state right now. The state is down for that link. But then the link comes up and the link state changes. We're going to go into the init state, let's say on R1, and we're going to send a hello message. We're using the hello protocol, sending a multicast out to 224.0.0.5, the all OSPF routers multicast address. We send this hello message over to R2. And R2, it's now also in the init state, and it says, I received this hello message from R1. But as we look at the contents of this hello message, R2 notices that I'm not listed. R1 does not know that I'm its neighbor. My router ID is not in that hello message. Well, R2 is going to send a hello message back to R1, including its router ID, and including router R1's router ID that R2 just learned. So now R1 says, I received this hello message from R2, and it knows me. I'm listed as one of its neighbors. Now, this interface on R1, it goes into the two-way state. We enter the two-way state when we receive a hello message, and our router ID is included in that hello message that we received from our neighbor. And now that we have learned the router ID of R2, when we send a hello message back to R2, now R2 sees itself in the hello message, and R2 can now go into the two-way state itself. While we're in this two-way state, that's where the designated and backup designated router election takes place. If needed, on some types of OSPF networks, we're not going to elect a DR, but if we are, it's in this two-way state where that election takes place. And if these routers are going to become adjacent, they need to exchange database information. And for this database information exchange to take place, we need to decide which one of these routers is going to be the primary router and which one's going to be the secondary. This election, different than the DR-BDR election, but this election as to who's the primary and who's the secondary, this election takes place in the X start state, and it's the router with the highest router ID that becomes the primary, and it starts this database exchange of information. And when that starts, we go into the exchange state, and the primary router is now going to be sending these database description packets over to the secondary router. The secondary router sends an acknowledgement that it got those database description packets. But what exactly is in a database description packet? The database description packet contains a list of all of the known LSAs, all of the LSAs known by our neighbor. And if R1 receives a list of LSAs known by R2, and R1 seems to be missing one, it needs to go get that missing LSA, and vice versa. R2 might need to get a missing LSA from R1. And when we're trying to fill in the missing pieces of our puzzle, we're in the loading state. This is where the routers can query one another, and we're going to be using link state request LSRs for this. We're going to be sending LSRs to the other router to get missing LSA information. How are LSA sent? Remember, an LSA is not itself a packet. An LSA is simply a collection of information, and that information is sent inside of an LSU, a link state update. Once we've filled in all of the missing pieces to the puzzle, we have identical link state databases on both routers. We've now reached a fully formed adjacency. Different routing protocols use different things to calculate their metric. In other words, how good is one route compared to another route? OSPF uses cost, and cost is a function of bandwidth. And to understand how cost is calculated, we need to understand the reference bandwidth. We've got a default reference bandwidth of 100 million bits per second, in other words, 100 megabits per second. And using the reference bandwidth, we can calculate cost by saying the reference bandwidth divided by the interface's bandwidth is the cost. You see, cost is cumulative. If PC1 on screen wants to get to PC2 on screen, what would be the cost? Well, we would have to add up the outgoing interface costs on each router to get us from PC1 to to PC2. And notice we've got a couple of different paths, don't we? We could go from R1 to R2 to R3. If we did that, we would be going over fast Ethernet, 100 megabit per second links all the way. There's what appears to be a shorter route in terms of the number of routers we have to transit. We could go from R1 directly to R3 and then go out to PC2. That's over a 10 megabit per second link, however. That's a slower link. We would probably prefer to go from R1 to R2 to R3 because we're staying at fast Ethernet speeds. Let's go through the math together. What would be the cost as we're leaving R1 going up to R2? Well, the reference bandwidth is 100 megabits per second. Our interface speed is 100 megabits per second. 100 divided by 100 is 1. We've got a cost of 1 as we're leaving R1 going up to R2. And using that same calculation, we have a cost of 1 because it's a 100 megabit per second link. We've got a cost of 1 on R2's outgoing interface going down to R3. We get down to R3 and now we need to go out to switch 2. That's another 100 megabit per second link. So again, the cost is 1. And that means our total cost, if we go the path from R1 to R2 to R3, it's going to be 1 plus 1 plus 1. It's a total cost of 3. However, we could go from R1 directly to R3. If we do that, we're going over a 10 meg link as we're leaving R1. What's the cost there? The reference bandwidth is 100 megabits per second. Our interface bandwidth is 10 megabits per second. 100 divided by 10 is 10. We've got a cost of 10 as we're leaving R1 going over to R3. And we've already calculated the outgoing interface cost of R3 going down to PC2. That is 100 divided by 100. That's simply a cost of 1. But if we add these two numbers up, if we go from R1 to R3, the cost is going to be 10 as we leave R1 plus 1 as we leave R3. 10 plus 1, that's 11. And as a result, we're going to prefer, based on our cost calculations, we're going to prefer to go from PC1 into R1, up to R2, down to R3, and finally out to PC2. That's the way OSPF does its cost calculation. However, we could run into an issue if we had higher interface speeds. Let's bump up the interface speeds a little bit. Now let's say between R1 and R2 we have a 1 gigabit link. Between R2 and R3 we've got a gigabit link. And we've got a fast Ethernet link between R1 and R3 and fast Ethernet going out of R3. If our reference bandwidth is still set to the default of 100 megabits per second, what is the cost as we're going from R1 up to R2? Well, it's the reference bandwidth of 100 megabits per second divided by the interface bandwidth of 1000 megabits per second. That comes out to 1/10. The cost value has to be an integer. We cannot have a cost value of 0.1. We've got to round up to 1. This means that by default, a 1 gigabit link is going to have a cost of 1. The outgoing interface on R1 has a cost of 1 going up to R2. Using the same math, we've got a cost of 1 going from R2 down to R3. And now, as we're going out of R3's fast Ethernet interface, the reference bandwidth is 100 megabits per second. The interface bandwidth is 100 megabits per second. 100 divided by 100 is 1. Are you starting to see the issue here? We're not distinguishing between a 1 gig link and a 100 meg link because the reference bandwidth is set to only 100 megabits per second. Well, let's continue with the scenario. With a path from R1 to R2 to R3, that's going to be a cost of 1 plus 1 plus 1. It's going to be a cost of 3. What if we go out of R1 directly over to R3? It's a 100 meg link. It's slower than the 1 gig link we could have used, but because our reference bandwidth is 100 meg and this link is 100 meg, it's a cost of 1, and it's a cost of 1 as we go out of R3 as well. That means if we go from R1 directly over to R3, our cost from the perspective of OSPF with a reference bandwidth of 100 meg, the cost is only 2. It's 1 plus 1. It appears to OSPF with this default reference bandwidth that we have a lower cost path by going from PC1 up to R1 and directly over to R3 and then down to PC2. We can look at the topology and see that that's a suboptimal path. We could have taken a 1 gig route from R1 to R3 going via R2. The issue is our reference bandwidth was set too low. How do we fix an issue like this? Well, to address this issue, which is going to be more and more common on today's networks as we have higher and higher interface speeds, is we need to set a higher reference bandwidth. We can do that in router configuration mode. In fact, when we get into the OSPF configuration videos later, I'll show you how to do this. But here's the syntax. In router configuration mode, we can say auto-cost space reference-bandwidth space and give a value. The units of measure are in megabits per second. The default is 100. And the question comes up at this point, what should my reference bandwidth be? Obviously, if I've got gig links in my network, 100 meg is too slow. It's going to make 100 meg links look identical in terms of cost. That's not good. What do? Do we just set it to 1 gig? Well, that's fine for today, but maybe next month, maybe next year, we're running 10 gig links. Suddenly we're in the same situation again. Should I make it 100 gig? We could do that. That's going to allow for some future growth. In fact, some people might look at this and say, well, set it to the maximum. If you use context-sensitive help, you see that the maximum is a little bit over 4 terabits per second. Why not just set it to the maximum? That's going to accommodate for lots of future growth. Well, there's an issue if we set this value too large. And the issue stems from how big an OSPF cost value can be. Cost is a 16-bit value. How big can a 16-bit value be? Well, 2 raised to the power of 16 is 65,536, but the numbering starts at 0. So the maximum cost we can have is 65,535. And the reason I bring this up is if we set our reference bandwidth too high, many of our slower link speeds, maybe our WAN links in our network, they're going to start appearing to have the same cost. For example, if I set my reference bandwidth to 10 gigabits per second, in other words, 10,000 megabits per second, if I had a WAN link that was running at 64K, if you do the math, and we have 10 billion divided by 64,000, that value is going to be greater than our maximum cost value of 65,535. If we had a 128K link, 10 billion divided by 128,000, that's also going to be greater than our maximum cost value. And as a result, a 64K link will have the same cost as a 128K link. So it's really a balancing act. You need to look at your network and understand if you make this reference bandwidth too high, you could cause some of your slower speed links to start having identical costs. But if you set the reference bandwidth too low, then you run into the situation we just saw where you've got some of your higher speed links running at different speeds, but they're both high speed links like fast Ethernet, 1 gig Ethernet, maybe 10 gig Ethernet. You've got those appearing to have the same cost. So it's a balancing act. You do want to accommodate for future growth, but you don't want to mess up existing cost calculations. So you need to look at this on a case-by-case basis. Hopefully, once we start to get into gig links and 10 gig links, hopefully we've largely moved away from the 64K and the 128K links. So hopefully that's not going to be an issue. In this example, I've decided to set my reference bandwidth to 100 gigabits per second. In other words, 100,000 megabits per second. If I do that, the cost, as I leave R1 going up to R2, the cost is going to be 100 gig divided by 1 gig. That's a cost of 100. Same thing as we leave R2 going down to R3, we've got a cost of 100. As I leave R3 going out toward PC2, that's 100,000 meg divided by 100 meg. That's going to be a cost of 1,000, which means that we have a cost of 1,000 if we're going from R1 directly to R3, because that's a 100 meg link. Let's add up the costs using these two different paths. If I go from R1 up to R2 down to R3, I've got a cost of 100 plus 100 plus 1,000, a grand total cost of 1,200 via that path. If I go from R1 directly to R3, 1,000 plus 1,000. We've got a grand total cost of 2,000. Now, because we have set our reference bandwidth to a higher value, we're now distinguishing between 1 gig links and 100 meg links. Now, we're going to take the optimal path. We're going to go from R1 up to R2, down to R3. This is something to keep in mind for the real world as we're starting to see more and more gig links out there.